Hi, Assalamualaikum. Welcome back to my channel, Physics for 5 KSSM. Today we continue Chapter 7, Quantum Physics, on topic 7.3 Einstein Photoelectric Equation. In my video, I will discuss 6 learning standards. The first one, state minimum work function needed by a metal to emit an electron using Einstein equation. Explain threshold frequency FO and work function W. Determine work function of metal W equals to HFO. Solve problems involving Einstein equation for photoelectric effect. Explain production of photoelectric current in photocell circuit. Describe applications of photoelectric effects. Let's get started. Einstein photoelectric theory. In 1905, Albert Einstein introduced a photoelectric theory that successfully explained all the characteristics of photoelectric effect in related experiments. He was awarded the Nobel Prize in 1921 for his achievement. This theory is named Einstein's photoelectric theory. Einstein applied Max Planck's idea of energy quantum. He suggested that energy is carried by light particles called photons. Means energy is in discrete form. The energy of each photon is directly proportional to frequency of light f and can be determined by the following equations. Energy of a photon, we have discussed earlier, E equals to hf, where h is Planck constant. The value is 6.64 times 10 to the power of negative 34 joule second, and f is frequency of light. Each quantum of light is discrete packet of energy, known as photon. There are many energy packets of photon in a beam of light that shines on the metal surface. When a photon arrives at the metal surface, the photon energy will be fully absorbed by an electron in the metal. This minimum energy or work function is used to release the electron from the metal, and the extra energy will become the kinetic energy of photoelectrons. In other words, we can say that a photon will cause one electron to be emitted or produce one photoelectrons. As you can see from here, a beam of light consists of many photons. If we have 3 photons here, it will be absorbed by 3 photoelectrons, or 3 electrons will be emitted. You can see from this one, when light is shined onto a metal surface, the energy required for electron to be emitted to the surface, we call it work function. If the energy is greater than the work function, the electron will gain kinetic energy, and it will move further from the surface of metal. Let's discuss about electrons on a metal surface. Photon energy is energy of a photon is equals to minimum energy required to release a photoelectron plus maximum kinetic energy of photoelectrons. So we have this equation, E equals to W plus K maximum. Energy of photon E equals to hf. W is work function, and K max equals to half mv squared maximum. So from here we can write one equation for kinetic energy of an electron, half mv squared maximum equals to hf minus W. So this equation is known as Einstein photoelectric equation. Actually, this equation is according to principle of conservation of energy. Means energy of photon fully used as work function and kinetic energy maximum of photoelectron. Okay, let's look at definition for work function and threshold frequency. Work function W is the minimum energy required for a photoelectron to be emitted from a metal surface. threshold frequency, FO, is the minimum frequency for a light photon to produce photoelectric effect. Means frequency of light must reach this value, or at least equals to this value, FO, for photoelectric effect to occur. Let's look at the graph here. The graph of Kmax against frequency. The graph is a straight line with a positive gradient and not passing through the origin. As you can see here, the value of Kmax increases when frequency is equal or greater than FO. When F equals to FO here, you can see the value of Kmax equals to 0. The threshold frequency FO is the value of intercept on the frequency axis. You can see at this value, the value of Kmax start to increase when frequency greater than FO. Now let's look at the Einstein photoelectric equation again. At the threshold frequency FO, photoelectrons are emitted without any kinetic energy. Or we can see when F equals to FO, energy of photon just enough for electron to be emitted and stay at the surface. There's no extra energy. That's the reason why kinetic energy maximum equals to 0. Thus, from the formula of Einstein photoelectric equation, Kmax equals to 0 equals to HFO minus W, because F is equals to FO. So we get W equals to HFO. The work function equals to the product of Planck constant and threshold frequency. So next, what we do, substitute the value of work function equals to HFO into the Einstein photoelectric equation again. So we get K maximum equals to E minus W. Energy of photon, HF minus W. So in this case, W equals to HFO. So we get here half mv squared maximum equals to HF minus HFO. Factorize H. Thus we get half mv squared maximum equals to H bracket F minus FO. So from this general equation, we can say that when F equals to FO, means the frequency of light equals to threshold frequency of the metal. So this one will become 0. Or we can say kinetic maximum equals to 0. That's the reason why here, when frequency equals to FO, the value of Kmax equals to 0. From here, we can say photoelectric effect exists when frequency is larger or equals to FO. And the electrons will gain kinetic energy when frequency of light is greater than threshold frequency of the metal. The relationship between work function and threshold frequency of a metal can be determined by a relationship W equals to HFO. Photoelectrons will acquire kinetic energy when light frequency exceeds threshold frequency, means F greater than FO. The higher the threshold frequency of metal, the higher the work function. This means that minimum energy required for photoelectric effect to occur is higher. Or we can say different metals have different threshold frequencies. So this one is the graph Kmax again frequency for different type of metal A, B, C. As you can see, these lines are parallel lines, means they have same gradient. All the lines here intersect at x-axis at one point that we call threshold frequency of the metal. So from here we can say threshold frequency of A, B and C are not the same. So it depends on the type of metal. Okay, let's look at the diagram here. Diagram here shows how intensity of light affect number of electrons emitted, or we can say the value of current that produced in the circuit. By using this cell photo, we can show what factors that affect the magnitude of current flow in the circuit. We have discussed earlier, intensity affects number of photons reach the metal surface. When the intensity of light is higher, means more number of photons will reach the metal surface. Thus, the number of photoelectrons emitted also increases. When number of photoelectrons emitted increases, means more number of electrons will be attracted to anode. The larger charge flow in the circuit will result in greater current. Thus, we can say the current flow in this photocell is influenced by intensity of light. Means the higher the intensity of light shine onto the metal, the higher the current flow in the circuit, due to more number of photoelectrons emitted. Okay, the same circuit also shows here. You can see clearly from here. Okay, when light is shined onto the metal surface, let's say 2 photoelectron emitted, it produces the current here. That recorded by milliammeter. You can refer to activity 7.8 in your textbook. Aim to determine work function of metals using formula. Using Einstein equation, Kmax equals to Hf minus W. If Kmax equals to 0, means frequency of light equals to threshold frequency of the metal. So from here we get W equals to HFO. We have discussed that one earlier. So you can see here there are different type of metal here, and their corresponding threshold frequency FO. The value here should be 10 to the power 15 Hertz. The work function W equals to HFO, so you just substitute the value of Planck constant and threshold frequency to calculate the work function for each of the metal here. So the work function, it depends on type of metal used. Thus, we can say different material have different threshold frequency and also different work function. When frequency of light equals to threshold frequency of the material, photoelectrons emitted to the surface, or F equals to FO. Kinetic energy maximum equals to 0. When frequency of light more than threshold frequency, F larger than FO, photoelectrons emitted and gain kinetic energy maximum. This one is based on the Einstein photoelectric equation. Let's look at some problem solving using Einstein photoelectric equation. Based on the Einstein photoelectric equation, we have this formula. Energy of photon E equals to work function plus K maximum. K maximum is kinetic energy maximum. Kinetic energy maximum equals to half mv squared. When we discuss about one photon, energy of one photon E equals to hf, means kinetic energy here is kinetic energy of an electron, means one electron or photoelectron. Work function equals to HFO. Let's look at example 1. A blue light with frequency 6.67 times 10 to the power 14 Hz is shone onto the clean caesium metal surface. What is maximum kinetic energy of photoelectrons emitted? Given work function of caesium is 3.43 times 10 to the power of negative 19 joule, and the Planck constant also given. Okay, so what formula that we should use? So in this case, we want to find K maximum. Thus, applying Einstein photoelectric equation, energy of photon equals to work function plus kinetic energy maximum. Calculate the work function. The work function is given already, no need to calculate. So you calculate for energy of photon, hf. The f is frequency of light. Okay, so this one is hf equals to work function plus K maximum. Thus, K maximum is equals to energy of a photon minus work function. So we get 9.92 times 10 to the power of negative 20 joule. So this one is one example of using Einstein photoelectric equation. Look at example 2. Figure shows change in kinetic energy of photoelectrons released from lithium from different light frequencies. Determine the threshold frequency from the graph and calculate work function of lithium. Planck constant H given. So in this question, we want to calculate the work function. So the formula is W equals to HFO. The value of FO is determined from this graph, as we know that K maximum equals to 0 when frequency equals to FO. Intersect of the graph here at f-axis showing that K maximum equals to 0. Thus, the value of frequency here is threshold frequency. So we just read from the graph here equals to 5.6 times 10 to the power 14 Hz. So that one is threshold frequency of lithium. Using the formula work function W equals to HFO, thus we get this value for work function of lithium. Example 3. What is the maximum velocity of photoelectron emitted when monochromatic light lambda 550 nanometer is shown on a metal which has a work function of 2 electron volt, given Hc, and 1 eV, mass of electrons, also given. So in this one, we want to calculate speed or maximum velocity of photoelectrons. Remember the formula, okay, of kinetic energy maximum. Okay, so firstly, we want to calculate what is energy of a photon. Energy of a photon is E equals to hf. But here we don't have f. Given is wavelength. To calculate f using the formula C divided by lambda. Okay, unit given is EV nanometer for the Hc here. So the nanometer above and below can be cancelled. Means the wavelength no need to change to meter, because here given is nanometer, the H is C. Okay, so you get 2.26 eV. Okay, energy also can be written by using this unit, electron volt. Also given the relationship here, 1 eV equals to 1.6 times 10 to the power of negative 19. Okay, now apply Einstein photoelectric equation. K maximum equals to energy of photon minus work function. So from here is energy of photon 2.26 minus work function 2 eV. So we get 0.26 eV. In order to calculate the velocity, the unit for velocity is SI unit. Thus we need to convert this energy to joule. So what you do, multiply with this factor. So half mv squared maximum equals to 0.26 eV multiply 1.6 times 10 to the power of negative 19. So the unit will become joule. Okay, now we calculate velocity, or maximum velocity equals to square root of 2 times E, okay, divided by m. This is mass of 1 electron. So we get 3.02 times 10 to the power 5 meter per second. Okay, so we use mass of 1 electron because the energy supplied here is energy of a photon. As we discussed before, a photon will cause 1 electron to be emitted. So 1 electron here, we can say, represent the whole photoelectrons emitted by the light. Example 4. When photocell is shown on with a red light, lambda 1, and a blue light, lambda 2, a maximum kinetic energy of photoelectron emitted by blue light is 2 times that of the red light. What is the work function of the photoelectric material in the photocell? What is the threshold frequency of the photoelectric material? Remember this graph. Just now we discussed about K maximum against frequency. As we know, frequency is inversely proportional to wavelength. So we can also plot a graph of K maximum against 1 over lambda, and we get the same shape of line. But intersect here is not value of frequency, but the value of 1 over lambda. If we have graph of K max against frequency, the point here shows threshold frequency. Thus, for this graph, this one shows 1 over threshold wavelength, 1 over lambda naught. Okay, wavelength of red light, lambda 1, given lambda 2. Maximum kinetic energy of red light, let's say, is K1, given for blue light is 2 times that of red one. So K2 equals to 2K1. Line constant is given. Let's say the work function symbol is W. Speed of light also given. H is given. From the Einstein photoelectric equation, energy of photon equals to work function plus kinetic energy. Frequency is not given. Here is given lambda. So we can use the formula Hc divided by lambda equals to W plus K. And then for lambda 1, we just substitute the value of lambda 1. There is a red light. Okay, so we get this is equation 1. And then substitute lambda 2. Okay, blue light, blue light. So we get to equation 2. Okay, what we do, K2 equals to 2K1. Okay, just substitute. Okay, and then some mathematical operation. Equation 1 multiply 2 minus 2. Okay, equation 1 multiply 2 minus 2. So we get this one. Okay, simplified equation. So we get this one minus this one, w minus w, k1. This one multiply 2, equation 1, so it become this one times 2, w times 2, k1 times 2. So minus, we can cancel the 2k1, so we get w 9.8 times 10 to the power negative 20 joule. B, threshold wavelength. So using the formula W equals to HFO, FO equals to C divided by lambda O. Okay, so from here we get lambda O equals to 2.03 times 10 to the power of negative 6 meter. So lambda O equals to C divided, frequency or threshold frequency FO equals to C divided by lambda O. So we get lambda O from this equation. Okay. That's all my video today. I will continue in my next video for the next topic, generating photoelectric current in photocell circuit and application of photoelectric effects. Thank you for watching. Bye.